This lecture discusses Chapter 16. In this chapter, you will learn the basic properties of traveling waves. Mechanical wave is a disturbance that is created by a vibrating object and subsequently travels through a medium from one location to another, transporting energy as it moves. Mechanical waves travel only within a material medium, such as air or water. Two familiar mechanical waves are sound waves and water waves. Electromagnetic waves, from radio waves to visible light to X-rays, are a self-sustaining oscillation of the electromagnetic field. Electromagnetic waves require no material medium and can travel through a vacuum. The mechanism by which a mechanical wave propagates itself through a medium involves particle interactions. One particle applies a push or a pull on its adjacent neighbor, causing a displacement of that neighbor from the equilibrium or rest position. As a wave is observed traveling through a medium, a crest is seen moving along from particle to particle. This crest is followed by a trough that is in turn followed by the next crest. In fact, one would observe a distinct wave pattern in the form of a sine wave traveling through the medium. This sine wave pattern continues to move in uninterrupted fashion until it encounters another wave along the medium or until it encounters a boundary with another medium. This type of wave pattern that is seen traveling through a medium is sometimes referred to as a traveling wave. Traveling waves are observed when a wave is not confined to a given space along the medium. The most commonly observed traveling wave is an ocean wave. It is, however, possible to have a wave confined to a given space in a medium and still produce a regular wave pattern that is readily discernible amidst the motion of the medium. For instance, if an elastic rope is held end to end and vibrated at just the right frequency, a wave pattern would be produced that assumes the shape of a sine wave and is seen to change over time. The wave pattern is only produced when one end of the rope is vibrated at just the right frequency. When the proper frequency is used, the interference of the incident wave and the reflected wave occur in such a manner that there are specified points along the medium that appear to be standing still. Because the observed wave pattern is characterized by points that appear to be standing still, the pattern is often called a standing wave pattern. A transverse wave is a wave in which the displacement is perpendicular to the direction in which the wave travels, such as the motion of a string that was flicked from one end to the other. In a longitudinal wave, the particles in the medium move parallel to the direction in which the wave travels. A wave transfers energy, but it does not transfer any material or substance outward from the source. The speed of a transverse wave on a string stretched with tension T sub s is the square root of the tension divided by the linear mass density, the mass divided by the length of the string. Here are a few problems for you to consider. Read the problems and we'll discuss these during next class. Here's our second problem. A graph that shows the wave's displacement as a function of position at a single instant of time is called a snapshot graph. It is simply a picture of the wave at one instance in time. Since a traveling wave moves, successive snapshots will show the wave propagating down the string. In the example, the wave is moving to the right at constant speed. The wave moves forward a distance delta x in a time delta t. A snapshot graph tells us where the wave is and how it varies with position, but only at one instant of time. It gives us no information about how the waves change with time. A graph that shows the wave's displacement as a function of time at a single position in space is called a history graph. For a wave moving from left to right, the shape of the history graph is reversed compared to the snapshot graph. Why? Think of a single position on the string. At some time t1, the edge of the wave reaches the position. In this case, the string begins to move upwards. It moves upwards quickly, and at a later time t2, the string has reached its maximum displacement. From t2 to t3, the string slowly returns to the original position. The snapshot graph tells us how things look throughout all of space, but only at one instant of time. The history graph tells us how things look at all times, but only at one position in space. We need them both to have the full story of the wave. The figure combines the snapshot graph and the history graph in one two-dimensional plot. The figure shows a sequence of time-ordered snapshot graphs. The example gives you a snapshot graph and asks what the history graph looks like for a position of 8 meters. Since the wave is moving at 2 meters per second, the wave does not reach 8 meters for 2 seconds after the time of the snapshot graph. The displacement for the first 2 seconds of the history graph must be 0. At 2 seconds, the displacement becomes negative. Since the minimum is at 3 meters, which is 1 meter from the start of the downward trend, the wave reaches a minimum 1 meter divided by 2 meters per second, or half a second later. So at 2.5 seconds, the history graph must have a minimum of -2 millimeters. The wave displacement then reverses direction. From 3 to 1 meters, the wave is ascending. This corresponds to a time interval from 2.5 to 3.5 seconds. For 1 more meter, the wave displacement decreases to 0, which is another half second in time. So the wave must reach 0 at 4 seconds. The original snapshot graph and the history graph at 8 meters must look like this. Right, here's another problem to be considered on Monday. Here's another problem. To visualize a longitudinal wave, we do not look at the transverse displacement, but motion along the direction of travel. Draw a series of equally spaced vertical lines to represent the equilibrium positions of particles before the wave arrives. Use information from the graph to displace the particles in the medium to the right or the left. The wave propagates to the right at 1 centimeter per second. In the wave at sporting events, the wave moves around the stadium, but the particles, the people, only undergo small displacements from their equilibrium positions. We will use the uppercase D to indicate displacement. Since the displacement depends on position and time, it is a function of two variables, x and t. So d of x comma t is the displacement of any position along the string at time t. A wave source that oscillates with simple harmonic motion generates a sinusoidal wave. The frequency f of the wave is the frequency of the oscillating source. If you are at a beach and waves come in twice per second, this means that there are 2 waves in 1 second interval. The time between waves must be half a second. The period of the wave is 1 over the frequency. The amplitude of the wave is the maximum value of the displacement. The maximum displacement is A, and the minimum displacement is minus A. A sinusoidal wave is periodic in space as well as in time. As you move from left to right along the frozen wave to the snapshot graph, the disturbance repeats itself over and over. The distance spanned by one cycle of motion is called the wavelength of the wave. Another problem for consideration. The figures show the relationship between wavelength and the period of a wave through 5 snapshot graphs of a sinusoidal wave at time increments of 1/4 of the period. 1 full period has elapsed between the first graph and the last, which you can see by observing the motion at a fixed point on the x-axis. Each point in the medium has undergone exactly 1 complete oscillation. During a time interval of exactly 1 period, each crest of a sinusoidal wave travels forward a distance of exactly 1 wavelength. The velocity of the wave is the distance traveled, 1 wavelength, divided by the time interval, the period. Since the period is 1 over the frequency, the velocity can be written as the wavelength times the frequency. Circular motion and simple harmonic motion are motions that repeat. Uniform circular motion projected onto one dimension is simple harmonic motion. The figure shows a ball glued to the edge of a turntable. The turntable executes circular motion. If light is projected across the turntable, the ball seems to execute simple harmonic motion. Since the position x of the shadow depends on the angle, we can write that x is a times the cosine of phi. If the turntable is turning smoothly, the angle is the angular velocity of the turntable times the time. But the frequency is the rate at which the ball's shadow moves back and forth, so there must be a relation between omega and f. In 1 period, the turntable goes through 360 degrees. So the angular frequency must be 2 pi divided by the period. Since the frequency is 1 over the period, the angular frequency is 2 pi times the frequency. As a convenience, we introduce another value, the wave number. The wave number is 2 pi divided by the wavelength. We can now write the general equation for a sinusoidal displacement. Since the wave speed was defined as the wavelength times the frequency, using the new values, the wave speed can be defined as the angular velocity divided by the wave number. We know that the wave speed is a property of the medium, while the wave frequency is a property of the oscillating source. We can then say the wavelength is a consequence of the wave of frequency f traveling through a medium in which the wave speed is v. The figures show the history graph of a wave at position x1 and the same wave at a snapshot graph at time t1. We have defined the wave as traveling to the right. If a wave is traveling to the left, it is indistinguishable from a rightward traveling wave going backwards in time. We simply change the direction of the time to define a wave traveling to the left. In the definition, there is a value we have not discussed, phi sub 0. This is known as the phase constant. It gives the displacement of the wave at time 0 and position 0. It is the initial condition of our traveling wave. The initial displacement is the amplitude times the sign of the phase constant. Since the string is in motion, we can define the velocity of the string at any point in time. The motion of the string is the displacement. The velocity is the derivative with respect to the time of the displacement. This velocity is the motion of the string. It is not the velocity of the wave on the string. Here's another problem for consideration. Section 16.4 deals with the wave equation of the string. We will not cover this section other than to say that all waves can be described by a second-order differential equation, which describes the propagation of oscillations at a fixed speed. The wave equation describes the motion of the string, provided the velocity is the square root of the tension of the string divided by the linear mass density. The solution of the wave equation is the displacement, d. In this problem, you are given the mass density of a string and the tension. The frequency of the input wave is 100 Hz. We must find the displacement equation for the string. To find the wave to travel to the right, the displacement equation is given. We need to find the amplitude, wave number, angular frequency, and phase constant. The initial condition, the oscillator, is that its maximum position displacement at t equals 0 seconds allows us to find the phase constant. The displacement is equal to a, so the phase constant must be pi over 2. The angular frequency is 2 pi times the frequency of 100 Hz, or 200 times pi radians per second. We can find the velocity of the wave since the tension in the string and the mass density are given. This yields 50 meters per second for velocity. Make sure all units are SI units. The wavelength is the velocity divided by the frequency, or 0.5 meters. The wave number is 2 pi divided by the wavelength, or 4 pi radians per meter. With an amplitude of 2 millimeters, 0.002 meters, the displacement equation is shown. Part B just requires us to use the displacement equation at a future time. At a point 2.7 meters away and 5 milliseconds later, the displacement is 1.6 millimeters. Sound is a longitudinal oscillation of molecules of air. The molecules oscillate back and forth alternately, compressing and rarefying the gas. It is often most convenient and informative to think of sound wave as a pressure wave. As the graph of the pressure shows, the pressure oscillates sinusoidally around the atmospheric pressure. This is a snapshot graph of the wave at one instant of time, and the distance between two adjacent crests, 2 points of the maximum compression, is the wavelength. For air at room temperature, about 20 degrees Celsius, the speed of sound is around 343 meters per second. Our ears are able to detect sinusoidal sound waves with frequencies between 20 Hz and 20 kHz. Higher frequency waves are called ultrasonic and are used in medical imaging and dog whistles. A light wave is an electromagnetic wave, an oscillation of the electromagnetic field. We will discuss what is oscillating in later chapters. All electromagnetic waves travel through a vacuum at a speed of light exactly 299,729,458 meters per second. And we use the symbol C to identify the speed of light in a vacuum. This spectrum is the electromagnetic spectrum. Electromagnetic waves exist at many frequencies other than our rather limited range that our eyes detect. This problem asks for the travel time for light traveling to Jupiter. The wave velocity is the speed of light, approximately 300 million meters per second. A 200 megahertz wave has a wavelength of about 1.5 meters. To calculate the time of travel, you need the distance to Jupiter, 800 billion meters, and divide by the speed of light yields about 45 minutes. Light waves travel with speed c in a vacuum, but they slow down as they pass through transparent materials, such as water or glass, or even, to a very slight extent, air. This is analogous to the wave traveling down a string with two different densities. When the wave strikes the heavier density string, the speed of the wave slows down. This is also true of light. When light enters a denser medium, it slows down. The index of refraction characterizes the speed of light wave in the medium. The index of refraction is the speed of light in a vacuum divided by the speed of light in the material. Since the speed of light is slower in the material, the index of refraction for a material is always greater than 1. Since air is not very dense material, the speed of light is only slightly smaller in air. For most problems, unless otherwise stated, use 1 for the speed of light in air. The speed of light in a diamond is less than half the speed in a vacuum. This, in part, accounts for the sparkle of a diamond. As with the string, the frequency of the wave does not change in the material. Since we know the speed does, this means that the wavelength must also change. The wavelength in the material is shorter than in a vacuum. Another problem for consideration. This problem asks for the speed of light in glass. Since the index of refraction of glass can be found in table 16.2, the speed of light in the material is the speed of light in the vacuum divided by the index of refraction, or about 200 million meters per second. The wavelength is the wavelength in the vacuum divided by the index of refraction, or about 400 nanometers. The number of waves in the glass at any time is the thickness of the glass divided by the wavelength of the light in the glass, or about 2,500 waves. Since we have not covered Chapter 14 yet, we will return to Section 16.6 later. However, we will need the result that the speed of sound in a material is the square root of the bulk modulus divided by the material's density. This problem asks us to find the speed of sound given the density and bulk modulus. It is a straightforward calculation showing the speed of sound in water is 1,480 meters per second, almost 4 times the speed of sound in air. It has been reported that someone underwater can hear a sound like a distant explosion, and when surfaced, will hear the explosion for a second time. A wavefront is an imaginary surface representing corresponding points of a wave that vibrate in unison. When identical waves having a common origin travel through a homogeneous medium, the corresponding crests and troughs at any instant are in phase. Any surface drawn through all the points of the same phase will constitute a wave front. Consider circular ripples spreading out on a pond from a rock thrown in. The lines that locate the crest are called the wave fronts. The curvature of an arc is defined as the reciprocal of the radius of a circle. When the radius is very small, the curvature is very large. When the radius is very large, the curvature is very small. If you observe circular wavefronts very, very far from the source, they appear to be straight lines. They have very little curvature. We can consider these waves very far from the source as a plane wave. In our displacement equation, the quantity kx minus omega t plus the phase constant is called the phase and is denoted by the Greek letter phi. So far, we have only considered the distance between crests or troughs of a wave. The distance is one wavelength, and the phase must equal 2 pi. Now we will consider looking at the phase difference between two different points on a wave. This is called the phase difference. The phase difference is the fraction of the wavelength between the 2 points times 2 pi. Another problem for consideration. This problem is looking for the phase difference between 2 points and the distance between 2 points separated by 90 degrees. Since we are dealing with sound, the wave speed is the speed of sound, or 343 meters per second. The corresponding wavelength for 100 Hertz sound is 3.43 meters. The phase difference for 2 points separated by 0.6 meters is 0.6 meters divided by 3.43 meters times 2 pi, are about 63 degrees. If the phase difference is 90 degrees, or pi over 2 radians, then the fraction of the wavelength is 1/4. 1/4 of a wavelength is 85.6 centimeters. It doesn't take long standing at a beach to realize that waves transfer power. You feel the waves against you, and the waves can knock you down. The power of a wave is the rate in joules per second at which the waves transfers energy. When play waves a power P impinge on an area A, we define the intensity I to be the power divided by the area. This problem asks for the intensity of a laser falling on a very small area. The power is the total power output of the laser, 1 milliwatt. The area is simply pi times the radius squared. This gives an intensity of 1300 watts per square meter. At the surface of the Earth, through the atmosphere, the intensity of sunlight is about 850 watts per square meter. At the top of the atmosphere, it is 1,365 watts per square meter. This shows the dangers of even a small laser pointer to damage the eyes. If a source of spherical waves radiates uniformly in all directions, then the power at a distance r is spread uniformly over the surface of the sphere of radius r. The surface area of a sphere is 4 pi r squared, so the intensity is the power divided by 4 pi r squared. This is a 1 over r squared law. the intensity decreases as 1 over r squared. We saw this in earlier chapters. The decimal system is a logarithmic unit used to express the ratio of two intensity values. There usually is a logical 0 point for our scale, indicated by I sub 0. Human hearing spans an extremely wide range of intensities. The faintest sound that humans can hear is 10 to the minus 12 watts per square meter, and thus I0 for hearing is 10 to the minus 12 watts per square meter. Table 16.4 shows the range of human hearing on a decibel scale. The faintest sound is 0 dB. Normal conversation is around 60 dB. Ear damage can occur around 120 dB. Another problem for consideration. This problem just inverts the definition of the decibel formula, solving for I. Find the intensity for one blender in watts per square meter. Double the intensity and then use the decibel formula again. Whenever an intensity level is doubled, the sound level adds 3 dB. The Doppler effect is the change in frequency or wavelength of a wave for an observer who is moving relative to the wave source. It is named after Christian Doppler, who described the phenomena in 1842. Here we see the source approaching Nancy at speed v sub s. It is receding from Pablo at the same speed. After a wave crest leaves a source, its motion is governed by the properties of the medium. The source could disappear and the sound would not change. For each of the time periods, 0, 1, 2, and 3, a spherical wavefront is emitted. Each wavefront in the figure is centered on a point from which it was emitted. The circles represent the wavefronts from the source at each of the positions. The wave crest from point 3 was emitted just as this figure was made, but it hasn't yet had time to travel any distance. The wave crests are bunched up in the direction of the source is moving and stretched out behind. The distance between one crest and the next is one wavelength. So the wavelength Nancy measures is less than the wavelength that would be emitted if the source were at rest. Similarly, Pablo, behind the source, sees the wave stretched out and the wavelength is longer than the rest wavelength. As the wave source approaches Nancy, she detects a frequency which is slightly higher than the natural frequency of the source. If the source moves at a steady speed directly toward Nancy, this frequency does not change with time. As the wave source recedes away from Pablo, he detects a frequency which is slightly lower than the natural frequency of the source. Again, as long as the speed of the source is constant, Pablo hears a constant frequency. The frequency heard is slightly different if the observer is moving or receding from a stationary source. These formulae give the perceived frequency for the 4 possible cases. The Doppler effect is responsible for the familiar change in pitch for a siren or train whistle as the source approaches you. The Doppler effect is also observed with electromagnetic waves, but with a different formula. The Doppler effect is used in Doppler weather radar to detect motion of clouds. The Doppler effect is also used in police, aircraft, and military radar. Another problem to consider. This problem uses the Doppler formulae for the approaching and receding siren. The frequency and the speed are not known, so 2 equations must be used to find the speed. The rest frequency is the same in both cases. By subtracting the 2 equations, the speed of the police car can be found. 34.3 meters per second, or about 70 miles per hour. Shown is a Hubble Space Telescope picture of a quasar. Quasars are extraordinarily powerful and distant sources of light and radio waves. This quasar is receding away from us at more than 90% of the speed of light. Any receding source of light is redshifted. Any approaching source of light is blue shifted. The two formulae given the wavelength for the receding or approaching source. If you define the receding source as having a positive velocity and the approaching source as having a negative velocity, the single formula for the receding source can be used. Since this is light, we use the Doppler formula for a receding source. Since the rest wavelength and the observed wavelength are known, the missing component is the recessional velocity, which is 15.6 million meters per second. Here's the problem that we will consider in next class. Here's another problem for next class. For next class, we will review all the problems presented in this lecture. We will have a lab on the speed of sound. Homework for this chapter is available on Mastering Physics. You can go to Blackboard and sign up for Mastering Physics now. See you on Monday.